Hello everyone. We are excited to present Victoria today, who will be talking about her work on retrieval-augmented dual instruction tuning. And just to introduce Victoria, so Victoria is a research scientist at Meta's foundational AI research team, FAIR. Her primary research interest centers around development of intelligent systems capable of efficiently processing vast amounts of information and assisting human in knowledge-intensive tasks, combining parametric and non-parametric approaches. Her most recent work focuses on integration of large language models with neural information retrieval. Prior to Meta, she was at Salesforce Research, where her work areas such as where her work encompass areas such as language to code generation, natural language interfaces, and question answering over structured data. So yeah, I think Victoria, you can start.
Thanks, Jay, for the introduction, and thanks everyone for joining this morning. So today I'm going to talk about our recent work, retrieval-augmented dual instruction tuning, which is joint work with my awesome colleagues at Meta. So if we took a look at the large language model, by the way, so I'm happy to take questions during the presentation, so feel free to interrupt me and unmute yourself. So if we take a look at the landscape of large language models in 2023, so large language models has been introduced about more than 2 years ago, and we have really seen the rapid development in this field. And in 2023, we have been witnessing products being released by companies which are touched millions of users. And so far, if we use large language model powered assistant, we are probably familiar with the concept of retrieval augmentation, because pure parametric form of large language models right after pre-training suffers from some limitations such as knowledge cutoff, and retrieval augmentation can be an effective way to supplement external knowledge for these type of models to help users in various downstream tasks. So besides overcoming the knowledge cutoff, I also want to motivate why we would need retrieval augmentation using a different example. So for example, sometimes, so we might see the users asking a question. So actually, apologize for a mistake on the slide. So I think the question should be, why does, so what food can I eat to take in more vitamin Ds? And so nowadays, the assistant will probably generate a long form answers like below. So it will list it will enumerate a list of foods which potentially has vitamin Ds, and it will supplement it with certain statistics. So however, as a user, typically once we read this long form of information, it is difficult for us to digest, okay, should I trust this information? Or whether they are accurate, if I'm seeking for certain things like nutrition advice, can I actually follow them safely? So, and imagine if the language model now has access to non-parametric memory, then it is possible to back up any statement it generated with some real-world document links. So for example, here we can see that the first statement is actually being able to be backed up by a real web page with a table on the page, and it will show a list of nutritious food and the actual vitamin D ratio in this type of foods. And we can see that. And then if the user is able to trace to that link based on from this generation, they will have more confidence in the language model answer. And similar for the second answer, the user is able to similarly trace where I generate these materials. So based on this example, we see that besides just supplementing knowledge cutoff, another important effect of having access to non-parametric memories, such as a vector database or a retriever, is we are able to ground the content generation of the language model and mitigate hallucination. And also, by doing this, we improve the user trust. And by doing this, we are able to supplement knowledge that is possibly beyond the pre-training cutoff. So once we know the importance of having non-parametric memory, so I want to go into a brief history of the combination of retrieval augmentation with large language models. So using retrieval augmentation for language models can be traced way back. Large language models has becoming popular. So the summary is also not intended to be extensive, because I think so I left out a few important works, but I want to start from this model called Retrieval-Augmented Generation for Knowledge Intensive NLP Tasks. So because I think this is a paper where the name RAG has actually become popular, and is even basically adopted nowadays when people are combining retrievers and large language models. So basically, in the RAG paper from FAIR, it introduced the concept of retrieval augmented generation, and also it proposes an architecture which is using retriever to augment sequence to sequence model. And in this architecture, basically, retriever is added as a prior to the generation, and the entire generation can be optimized end to end, propagate all the way from the language model to the retriever. So fast forward, and so there is also continuous effort of combining retrieval with nowadays the further scaled autoregressive language models. So for example, one noteworthy work comes from DeepMind, which basically design a non-parametric memory implemented by shallow encoders, and couple it with the backbone language model using cross-attention. And this architecture is also trained. This architecture is also pre-trained. However, in this architecture, the authors use a freeze retriever, so that only the language model is updated and the retriever is initialized and freeze. So what really caught my personal interest about this paradigm is I think is some work which concurrently proposed at the beginning of probably this year. So one noteworthy work from Meta in this group is this model called Replug. So basically, people found that to actually combine retrieval and language model, we probably don't need very complicated customized architecture. We can simply taking an off-the-shelf retriever and take the retrieval content and just put it into the context window of the language model, and then let the language model perform something like a reading comprehension, and it is able to effectively extract information from these retrieved content. So this proposal is really simple, and it can effectively leverage off-the-shelf large language models and retrievers, which is typically nice features for building, especially real-world downstream tasks. And I think it has been getting really popular in the industry nowadays, especially powered by some special underlying infrastructure improvement. And also a remark on the Replug paper, because throughout the rest of the talk, so in our Ready to Work, we also used the framework very similar to this paper, is that so when it is handling retrieval with multiple documents, considering the context length restrictions of large language models, it does not perform concatenation of the retrieval documents, but instead it performs this type of parallel retrieval augmentation, which is taking each of the separate retrieved text chunks, prepended with the prompt of the language model, pass them through the language model separately, and then aggregate the results. So for our work, we really asked the question. So we saw some effectiveness of combining off-the-shelf language model and a retriever. Can we somehow improve their integration using some lightweight, cost-effective approach, which is fine-tuning? So here, through fine-tuning, we want to improve the ability of the language model to better utilize the retrieved content supplemented from the retriever. And we also want to use language model as a supervision agent to give the retriever feedback so that the retriever can return more contextually relevant content. So as I will show in the next few slides, so this can be done through a simple two-step fine-tuning approach. So a note I want to also make is that, so once we release our paper on arXiv, we actually noticed that there has been several related concurrent developments throughout 2023. So along the idea of improving the ability of large language models to better use retrieved content. So there is a paper called Search Augmented Instruction Learning, and there is another paper coming a little bit after our paper, which is called Self-Rec. So, and those are also interesting references to check out. So to understand our approach, let me use a running example. So here, which is the question I'm focusing on, which is so the user ask a question about like why their GPU is keeping on raising an error about XID 79 falling off the bus. And in this case, so given user instructions, it is issued to both the language model and the retriever. So the retriever will return a set of relevant documents. And in our case, we perform the parallel retrieval augmentation like what Replug does. And we basically take each of the retrieved passages and prepend it to the language model prompt and basically separately pass these augmented prompts to the language model. And it is worth noting that nowadays, despite leaps and bounds improvement of retrieval systems, we found that for practical problems, the set of documents returned by the retriever can be noisy. So for example, in this example, the first text chunks contain some useful information on explaining why XID 79 is falling off the bus. But like the second one, it's just some passages generic about the hardware market, which actually doesn't help answer this question. So for the retrieval-augmented instruction tuning, what we perform is a very simple procedure. So basically, we take the set of passages returned by the retriever, and we fine-tune the language model to output the correct answer, regardless of the correctness of the retrieved content. So as I will show later in our experiments, so basically by doing so, we enable the model to better extract information from the retrieved passage when the passage is indeed relevant. It also has a second effect, which is when the retrieved passages is noisy. So this procedure will effectively teach the language model to ignore the retrieved background and rely on its parametric knowledge to answer the question. And so a separate step we perform is a retriever fine-tuning. So basically, once we pass the augmented prompts through the large language model, the large language models will generate a score for the correct answer given these augmented prompts. And the intuition here is basically if a retrieved text passage enables the language model to generate a higher score for the correct answer, then likely this retrieved passage is relevant and effective. And if it actually doesn't induce higher probability from the language model for the correct answer, then likely this retrieved passage is noisy, and we probably should train the retriever to avoid returning it next time. So basically, the retriever fine-tuning step. In the retriever fine-tuning step, we design a supervision score, which is called a language model supervision score, which is basically a probability distribution normalized over the conditional probability of the correct answer given different passages. And we will minimize the passage ranking score. We will minimize the KL divergence between the passage ranking score from the retriever with this language model supervision score, so that effectively we promote the retriever to return passages that is more effective in inducing the correct answers from the language model. And in practice, we can carry out the retriever fine-tuning and the language model fine-tuning in separate steps. And we also show that just by doing these two simple steps and combine the resulting retriever and language model, we can get further gains. So this is basically the framework of the model. And we fine-tune this framework using a collection of data sets, which is formulated in this instruction tuning format. So here we collected about overall like 20, so about 20 to 30 different tasks. And so for the tasks, we focus on selecting those which is promoting knowledge utilization and also contextual awareness in the language models. So for example, here, like we cover in total 5 categories. So like including conversation, open domain question answering, reading comprehension, summarization, and chain of thought reasoning. And we use different sets of fine-tuning tasks for the language model and the retriever. Because, for example, for some tasks, such as summarization, it's essentially difficult to repurpose it for retrieval fine-tuning. So we take out these type of tasks for retrieval fine-tuning. Okay, so and we go to our experiment setup. So we initialize, so for our framework, we initialize the language model using the Llama series models. And without further specification, so typically we report results on the 65 billion, the largest Llama model. And so for the retriever, because we want to continuously update it, so we chose the dense retriever. And in particular, we initialize it through Dragon, which is a dual encoder retriever trained with contrastive learning objective and data augmentation, and has state-of-the-art performance on a set of different benchmarks. So we fine-tune the model, the language model, using the label loss, which is now commonly adopted in supervised instruction tuning. So basically, the label loss is we compute the language model loss, but for an instruction prompt, we only compute it on the output section of the prompt. So which basically we only compute the loss over the answer section of the input. And we also perform like example packing. And so basically this effectively allows us to fine tune over an effectively larger batch size. And for the retriever corpus, so we use a corpus which is similar to a corpus used in prior work called Atlas. And so this consists of like in total about 400 million text chunks we get from Wikipedia and Common Crawl. So we found that this is about the right size we can serve effectively for fast experiment iteration, and also offers enough diversity in the text chunks to kind of mimic like a real world open domain setting. So this is a quick remark on the Dragon retriever we use for the initialization of the framework. Like I mentioned before, so Dragon has demonstrated impressive trade-off between supervised downstream evaluation and also the zero-shot evaluation. And its performance as a dense model is comparable, is approaching some of the late interaction models. So, so we chose this model because of the efficiency and its strong performance. Okay, so a further remark on experiment setup is like for our fine tuning. So we typically choose top 3 retrieval passages to augment our fine tuning data. So for each of the fine tuning example, on average, we created 3 of these retrieval-augmented prompts. And so for inference, we take 10 retrieved passages from the retriever and perform the parallel retrieval augmentation and ensemble the results. So let's dive into the results. So we first benchmark our model and the baselines on a set of knowledge-intensive tasks. So which is a standard tasks for testing the not the knowledge memorization of models, covering QA and other things. So here we use MMU natural questions, trivial QA, and also a subset of the standard knowledge intensive benchmark. And here, so we observed that for zero-shot performance comparison, adding retrieval augmentation can significantly improve from the base llama model. And here we have two retrieval augmented models. One is a baseline we compare, which is basically combining the off-the-shelf llama model and the retriever, and the other is our fine-tuned approach. And so adding retrieval augmentation significantly improve over the base llama model, and we also show that basically using retrieval augmented fine-tuning, we are able to also further improve from the replug approach, which is combining off-the-shelf llama model and the retriever. So another observation is that for the 5-shot evaluation in this setup, so where basically we will show the model 5 demonstration examples, and for each of the demonstration examples, we pair it with the top 1 retrieved passages. And in this setting, we still see improvement from the retrieval augmentation. And also, like, we will see a consistent improvement from the retrieval augmented fine-tuning. But comparing with the fine-tuning setup, we notice that in the comparing with a zero-shot setup, we notice that in the 5-shot setup, the gain we are able to see from fine-tuning is less compared to in the zero-shot setup. So I think this is an interesting fact. But on the other hand, this has also been observed in our previous instruction fine-tuning experiments, where we saw that instruction tuning, especially when we don't specifically fine-tune the model to improve its ability to follow in-context examples, the improvement on in-context few-shot learning can be limited. So I think during this work, we observed this limitation again, and I think it could be like an interesting field work to further looking into this effect about like how we can using instruction tuning to not only significantly improve the zero-shot performance, but also like but also further improve the model's ability to follow in-context examples. So we also, besides the knowledge-intensive tasks, we also check the model on a set of common sense reasoning tasks. So in comparison here, the knowledge we test compared to the previous set of tasks is usually more commonly seen in the corpus, and like they include probably more frequent knowledge. And so here we basically benchmark the base llama model. So our model without using the retrieval, and also our full model using the retrieval. So here we see that both variations of our model is outperforming the llama baseline. And so this is good news, because one thing we want to check is that after we perform this type of instruction, after we perform this type of retrieval augmented fine-tuning, so is the fine-tuning approach still effectively preserve the parametric knowledge of the language model? So I think the second row here basically show that. So at least we don't see performance degrade on common sense reasoning tasks when retrieval is not used, and in fact we're seeing a slight performance improvement, possibly because of the general instruction tuning procedure. We also note that for these set of tasks, after we add a retrieval, we see a very small delta comparing to without adding the retrieval. So which is also possibly explained by the fact that these are common sense tasks. So possibly the required knowledge has been frequently occurred in the pre-training corpus, and the model has memorized them well in its parametric space. So this is our benchmark on the common sense reasoning tasks. So we further conduct an ablation experiment basically to test out. So we see some improvement, but whether the improvement comes from our particular retrieval augmented instruction tuning approach, or the improvement just comes from that we fine-tune the model, and we know that fine-tuning can effectively improve the model's performance on QA tasks, for example. So here, basically, on our dev sets, we conduct a comparison between our approach and the vanilla instruction tuning approach. So basically, vanilla instruction tuning approach refers to that we just take our fine-tuning set and without doing retrieval augmentation, just taking the instruction prompts and fine-tune the language model and see how the model performs. So here we basically see that indeed, just instruction tuning itself can significantly improve over the base language model. But on the other hand, so adopting our retrieval-augmented instruction tuning can further improve over vanilla instruction tuned model. Especially, we saw again when we use more retrieved chunks. So as I will show later in your qualitative results, so basically we found that like adding retrieval augmentation in this fine-tuning process, indeed it is able to make the model better comprehend relevant information, but also become more robust against the noise. So we think that that contributes to why we see like an even further improvement when we have top 10 chunks. And here, so on this data set, like even more prominently, we have observed the effect that both fine-tuning and retrieval-augmented fine-tuning is not really effective for in-context learning, at least on the set of tasks we benchmarked. So which we think is some interesting results which worth keeping in mind for. Okay, so we also did like ablations on our retriever fine-tuning strategy. And here, so basically I will show the most important axis, which is basically ablation on what data set we use for the retriever fine-tuning. So recall before, like I showed slides, which we select 10 high quality knowledge intensive tasks for the retriever fine-tuning. And in practice, we actually found that if we just fine-tune on the multitask data combined, so the improvement we get from the retriever is actually very small. So there could be a couple of reasons contributing to it. One is potentially because we already started from a very strong base retriever. And it's possible that so the data set we use don't actually offer much additional diversity and other information to the base model. And so we were seeking for some improvement. So one thing is taking inspiration from previous work. We know that unsupervised text can be effectively used for data augmentation for retriever fine-tuning because we can take a limited amount of unsupervised tasks and basically create a data augmentation to fine-tune the retriever to find relevant tasks for its prefix, for example. So we also conduct fine-tuning on the unsupervised text, which is about 900K text chunks we sampled from our pre-training data. And we found that just fine-tuning on the corpus data is more effective compared to fine-tuning on the multitask instruction data. And our final recipe is basically we did a blending of both the unsupervised training data and also the multitask training data for retriever fine-tuning. And we ended up using 5% of multitask training data in this combination. And that gives us the most robust and significant gains for our retriever. And so this is the recipe we used for our retriever fine-tuning data eventually. I think in the future work, it's definitely worth basically further investigating how can we improve multitasking fine-tuning for the retriever, because I personally feel that task data should be able to offer strong supervision signal, and it will be very interesting to further investigate how can we more effectively distill the supervision signal from task data. Okay, so I also want to show another set of very interesting results, which is related to the scaling law of our approach. So here, basically, so one remark on this sheet is that this set of experiments is conducted with the vanilla dragon model. So we didn't use our fine-tuned dragon. So and here, basically, the thing we want to test is the effect of retrieval augmentation language models of different sizes. So we take our retrieval-augmented fine-tuned language models across different size of the llama model, so including 7 billion, 13 billion, and 65 billion. And we benchmark them on many different tasks. So here, as the curves shown on the plot, the further thing we observe that is that retrieval augmentation is in general helpful across different model sizes, and also almost on all the tasks we tried, adding retrieval augmentation is effective. The second interesting observation is that typically retrieval augmentation can be more effective for smaller models. As on several of the tasks shown in the plot, we found that like the slope of increase for the 7 billion model is much more significant comparing to the improvement for the 65 billion model, for example. A third observation is that the effect of adding retrieval augmentation to different sized model is different across tasks. So what I mean by that is, so we see some of the tasks adding retrieval augmentation is very effective, and it even closes the gap between small models and large models. So for example, this zero-shot relation extraction tasks. However, on the other hand, for some of the tasks like hot-pot QA, which is multi-hop question answering and possibly requires more complicated reasoning and a combination of different retrieved evidence, we notice that adding retrieval doesn't complete the gap between smaller language models and large language models. So I think one thing which might shows that, so there is something intrinsically important about scaling the parameter size of language models, so which is possibly related to the reasoning capability of such models, and this part this part is cannot be totally replaced by just adding non-parametric memory. So this kind of shows that like basically improving non-parametric memory access versus scaling up and improve the dense model training, they are possibly complementary to each other. And when we're thinking about like improving language models, we should possibly thinking about improving both of them side by side. Okay, so I want to show some qualitative results. So here, basically, like we further look into some of the model predictions of the retrieval-augmented instruction-tuned model and compare it to the vanilla instruction-tuned model. And here it shows a question, and we also show the different model predictions and their corresponding scores. So here we observe something interesting, which is, so although I think in this example, we actually found that both the retrieval-augmented instruction-tuned model and the vanilla model is able to get the correct answer for a relevant text. And also they actually both suffered from a distraction from irrelevant retrieval. But if we look into the prediction score, we saw that, so basically for the retrieval-augmented instruction-tuned language model, it is able to be more confident when relevant information is present, in the sense that it predicts the correct answer, which with a higher probability. And when a distractor is present, it actually assigns the wrong answer due to the distraction with a much larger negative log likelihood, which indicates like much lower confidence compared to vanilla instruction-tuned model. So I think this pointing to the fact that retrieval-augmented instruction tuning is indeed effective in teaching the model to more effectively leveraging its context augmentation. And and there could be more interesting future work to be done in improving this access. With this, I will summarize the talk. So basically, with this talk, we show that fine-tuning language models with retrieval augmentation is an effective approach to improve the language model. It can also generate the supervision signal to improve the retriever. And most importantly, it can improve the integration between the two components. We also found that as a side observation, that scaling parametric capability of language models and retrieval augmentation can be complementary, because on complicated tasks, we don't see that just strengthening non-parametric memory access can close the gap between smaller models and larger models. And also, so while we present Reddit as an approach to kind of creating some tightly coupled retrieval-augmented models for certain domains, we think as a future step, it can also be just blended into the standard instruction tuning process, so that we can create overall better instructable models that is good at accessing external knowledge. So regarding future directions, I think there are many interesting future directions and improvements we can do on top of the model, but I think I will highlight two things. So one thing is we notice that in the current retrieval-augmented language modeling paradigm, there is vast space to improve the quality of the retriever. So which I think I know, like, folks at Cohere has also been actively working in this space. So basically, we found that for many tasks, we even just like taking from the standard NLP benchmark, the retriever rate we currently use doesn't generate much relevant text. And for example, for the hard copy QA task, actually for majority of the questions, we found that all of the returned passages are noise. And basically what the language model is doing is it's fighting against these noisy passages, and hopefully like it can use its parametric knowledge to get a better answer. So I think this is something we notice, and we think that improving the retrieval quality, it is a hard problem, but it is definitely a very important stage to improve the overall performance of retrieval-augmented language models. So on the other hand, so like there's a side remark is I think some people may think that, okay, so maybe for language models, like they function differently. So if even if the passage doesn't look relevant from a human perspective, maybe the passage is still relevant for the model to induce it to get a correct answer. So I think that might be true. So for example, like if we retrieve some remotely domain-related passages, maybe it will still help the language model to answer this question. But I think overall, from the perspective of improving accuracy and also even improving provenance, it is important for the retriever to just like become more accurate when it's trying to seeking information from the ocean of the web, for example. Okay, so another direction, which is so sometimes I think the problem of basically the retriever cannot find the relevant information might comes from that we are just not giving it very good queries. So for some of the tasks, again, like hotspot QA, it requires multi-hop reasoning, and usually it is hard to just find the exact relevant information if we search for the question as a whole piece. But this basically will require the system to function like a human. So like when a request comes in, how do I break the request down into smaller steps and maybe search for the relevant information for each of the smaller steps? So this has I think already has been an active research area, and I think we can definitely need like further push on this direction, which is basically creating system 2 type of retrieval-augmented language models, and basically to realize effective combination of retrieval and reasoning. So with this, I will wrap up my talk, and I'm happy to take questions. Thank you.
Yep. So thanks for the presentation. So one thing, I had a question right now. So let's say basically in retrieval, right, when you are retrieving documents, and maybe let's say you might have information that has changed over the temporally changed, right? So maybe let's say some documents are old, some documents are new, right? But still the document is relevant to the context, right? At least how do you think, or at least like maybe like in terms of the loss, or at least the ways like we can actually avoid or enforce some constraints, right? That model focuses on the relevant information, or like.
Yeah, I think this is a great question. So, which is related to in some sense, like it can be related to like maybe like my non-parametric data store is actually outdated, or it's not outdated, but it has information in there, but with some like temporal conflict. So I think if we just look into our particular framework, we actually didn't design the framework to particularly handle this to particularly handle this challenge, unless that we see that like unless that we say during the fine-tuning stage, the model has run into temporal conflicted passages, and we still fine-tune it to generate the correct answer so that it can handle this type of conflict implicitly. But this is just for our framework. So I think maybe as like future improvement, so we can possibly like so I think one thing is we can possibly so I think one thing is like I think it's possibly like to some improvement on the retriever side. So which is like so when it is like searching for relevant information, taking the temporal information into account, and probably like somehow like we just remove the documents that doesn't temporally match during the retrieval stage. I think it's also possible that like we can fine tune, so we can like improve the language model to become more robust. So for example, like if it sees certain temporal information in the retrieved passage, it is effective reasoning over that and realize it doesn't match the current temporal requirement from the instruction, and basically either disregard the passage or like perform some effective synthesis of the information.
I see.
Yeah, but I think that's a great question, and that's yeah, that's definitely a challenge that should be solved by such systems.
I see. Also, so right now, in let's say with the setup that you have, right? Maybe you first, let's say, fine tune the retriever, right, on like one specific domain, and later on, let's say you want to adapt this to some other domain, right? So, did you try some experiments where, let's say, maybe you first like do this fine tuning on more general domain, and then probably like do fine tuning on a very specific domain where you probably lose out some performance of retriever on, let's say, the general purpose domains, or at least like how do you still maintain the performance, or at least like while let's say improving on the other domains, right? Like I say over time, it's more like an online learning setup, right? Where maybe things would be new. Basically, we will encounter new things, right? But we still want our retriever to like learn to those, but also not forget to the ones right in the past.
Yeah, so I think that's also a great question. So, we didn't actually try that particular setup, but I think in our work, the designs, so when we are so we try to select like the fine-tuning data, which is hopefully is inducing like general reading comprehension ability of the language model. And also like for the retriever fine-tuning task, we're also trying to select the task which basically covers like diverse domains. So I think one perspective for this is like hopefully, so the fine-tuning process we have like, so when we are gathering the initial multi-task fine-tuning data set, it's more about improving the general capability of the model and the retriever versus like having them bias to specific domains. But as you mentioned, what if like now I have to fine tune on some specific domains and I got loose? So I think one thing is one solution could be like fine tune a different, just like perform different fine tuning for different domains. So for example, maybe we can do parameter efficient fine tuning on both the language model and the retriever. And basically that create customized fine-tuned language model and retriever just for that domain. And in that case, like basically we have another copy of the language model, which is still have its original capability.
I see. I see. And also, so right now, right, you mentioned that, let's say, like a retriever and like the actual model, right? Those can be fine-tuned or like tuned in independent steps as well, right?
Right.
So then let's say if I have my retriever right now and maybe there's some new model that's coming in, right? And I want to, let's say, plug the old retriever to that, right? So do you think that might like suffer from some biases or at least some, let's say, because initially your models were not like, let's say, specifically suitable. So both the components are not like jointly optimized, right? So do you think that sort of like setup works well in independent, like when you do independently and combine different things, or like do you think joint optimization is the most like more beneficial in general?
Right. So I think so. This is a great question regarding joint optimization versus independent. So I think in our experiment, so in our paper, there's a table I haven't shown. So which is we need to find that like separate fine tuning can be effective. So like the main reason we didn't choose joint optimization is due to the complexity. I think because I think people have so basically like thinking about like the complexity of like back propagating the loss to the retriever, and especially I think in our paper actually the loss is not so basically the loss is not like so basically the whole system is not differentiable, so we cannot just directly back propagate the loss to the retriever like RAG, but I think one potential improvement for our approach if we want to further improve the coupling of the retriever and the language model is we can potentially go for the iterative direction. So for example, so we can make basically the retriever and the language model fine-tuning steps iterative. And basically we perform like two-step fine-tune the language model, fine-tune the retriever, and then fine-tune the language model and iterate. So we initially plan to try this experiment, but like so yes, so we didn't try actually adding more iterations. I think that could potentially be a way to basically improve the performance, but also avoiding the complexity of doing joint training.
I see. I see. Also, so one more interesting, at least the scaling laws, right, that you had. So that it's clearly evident maybe that like having bigger models like definitely helps, right, in this case, like for retrieval. But also, so do you think where in this case bigger models are also, let's say, more susceptible to, let's say, adversarial perturbations, or at least maybe if the documents are more noisy, then at least they would be more prone to, let's say, just answering, like generating some answer, right? Instead of like rather than abstaining from generating any, like abstaining from generating an answer, right? Like so do you have any thoughts on how should one go about it? Like because yeah.
Yeah, I think that's a great question. So I think if I think so for the limitation we just mentioned, it could be so for off-the-shelf language model or like language model which is like conducted, so basically which is fine-tuned through without a retrieval augmentation. I think I could imagine they can possibly suffer from this. So maybe they are more easily affected by noise information in the context because they just probably have better context following ability and there's no signal to tell them so whether the current context in their context window is relevant or not. But I think, so first of all, at least in our experiments, we found that large models always give better. So on the task, we found large models performs better. They do give better performance. And I think maybe it's also so large language models can also be steered to avoid this type of noise when we conduct specific fine tuning like retrieval augmented fine tuning. So I think with retrieval augmented fine tuning, we show the model what is the noise case, and you should ignore information in this type of noise case. I think this is an effective approach, and we seem to find that it is effective, and it will make large models better.
I see. I see. And did you also maybe experiment with any parametric efficient approaches? So maybe like let's say instead of so right now you're doing full fine tuning, right, of the base model, right? So maybe using like let's say any parametric approaches and whether they have any limitations when let's say like to like or like compared to the full fine tuning or like specifically for this case?
Yeah, so we didn't try. So I mentioned that first, but I think it will work, but we didn't try it ourselves. I think part of the reason is because I think for us, we are still like trying to basically. So for this particular paper, we still try to inject the ability of comprehending context into the language model. So we think the full fine tuning is a more effective approach here. But I think for lots of like practical cases where maybe like so basically like we need to now fine tune a RAG so that like I need to have a model which can better answer questions for my internal documents, or like I need to have models which can better answer questions for code base. In this type of like very specific use case, I think parameter efficient fine tuning can be effective, because you can fine tune a small set of parameters and just make it sit there, and then you will have something which will be serving a specific purpose.
I see. Makes sense. Also, just one thing. So currently, I think you like first, let's say in your setup, right? Like have a retriever which generates a text, right? And then you concatenate that text with the query, right? And basically ask the answer, right? That is that like becomes a non-differentiable step, right? At least when you prompt the LLMs. So like, do you think like trying it with directly doing it the token fusing, or at least like maybe whatever the context that you get right from the retriever, and basically just embedding that context with the LLM and using it as a soft prompt or like tokens, right? Do you think that's a good idea or legacy, or any thoughts on that?
Sorry, Jay. So I think there's a bit of cutoff in the questions. So would you mind to repeat the question?
Yeah, sure. So one thing I was just wondering, right now, if you look at right, like the setup, basically you have like a retriever which gives you like let's say relevant document, right? And based on the document, you basically concatenate it with the question, right? So basically, sorry, query, right? So which becomes a non-differentiable step, right? At least like. So I was just wondering if this is a good idea, or maybe doing directly like token fusing is a good better idea. So maybe like let's say you directly get the retrieval context, right? Like basically some embedding vector, right? And maybe you have a query embedding vector already. You fuse it and basically do something like that. Do you think that's a like a very better idea, or like yeah, just like wondering if you have any thoughts?
Got it. So like you're saying like so you mentioned fusion of like the document vector and the query vector.
Yeah,
So
yeah.
I didn't fully understand the part where you say how these two will be fused.
Uh, so more like similar to so let's say in diffusion models, right? There have been like let's say you have different features that you want to let's say do right, induce, right? So what they do is like they let's say throughout different layers, right? They might have like this different like vectors, right? Like feature vectors or at least some style vectors, right? They will just fuse into the process, right? As they keep denoising. So I think one example is control net. uh, so yeah, which can give you very rich like image let's say generations, right, based on some text prompt that based on let's say you can steer away the model towards certain things, right? So I'm just wondering if let's say when you have a query, right, instead of showing the document at the very start, right, if you kind of come up with some similar approach where you basically do this token fusion, right, throughout intermediate layers, and maybe like first LLM let LLM generate right things, right, and then use this embedded document vector, right, in order to refine the generation, right, over like let's say the embedding space, right, or at least the embeddings.
Right. So I think I should understand it now. So I think so regarding the fusion approach,
Mhm.
this reminds me of retro from DeepMind. So which is like so I think they basically fuse the so it's basically they encoded the retrieval documents and like
Mhm.
using and then like it fuse the hidden states of the encoder with the language model through cross attention, and
Mhm.
it is done at like intermediate layers of the language model. So I think the architecture you mentioned it reminds me of retro. Um,
Mhm.
I
Yeah.
think I so we actually didn't conduct a head-to-head comparison of these two approach. So I I think basically the cross attention type style filtering sorry fusion, it is very interesting. It we can possible so um so I think the the difference here is, so for example, like when we are just like prepending the retrieved passage from in front of the prompt, I think in some sense we can also argue this is a very deep type of fusion, because like, so basically the large language model itself will jointly encode the context and the original prompt. It will go through many layers of self-attention. So actually, in some sense, I would argue this is actually like a more coupled integration compared with like using like a separate memory module and then couple it with a language model through cross attention. So I think one difference is probably like actually our approach, the RAG approach we currently use now, is actually more computationally expensive, because like basically the cross attention is handled through using the large language model itself. Like you enlarge the context, it actually makes the whole system more computationally expensive. But we found it is to be effective. It is conceptually simple. It reduces like people's basically mind burden of designing more complicated cross attention. So I like it. But on the other hand, I think it is like interesting to explore the retro type of fusion. But I think I predict the system could be harder to train, and because like we're using less parameters in the encoder, usually this is done like through a shallower encoder. Maybe initially we'll see actually inferior performance comparing to RAG approach if we spend the similar amount of like training data. But on the other hand, like maybe so this approach, so like basically the cross attention type of filtering can offer some interesting efficiency gains like further down the road. I think that could be happening, and probably like people can also like combine these two type of approach. Then first using like the retro style augmentation to handle a large set of text chunks, and then like for the selected ones, like we further use like this language model context augmentation. I think some people has already proposed that actually.
I see. Interesting. Yeah, because I think the self-fact paper at least like tries to maybe, let's say, introduce this like critic tokens, right? At least where they just like do this retrieval, like, and then we see, let's say, again predicting whether they should retrieve or not, right? So at least that's sort of maybe somewhat similar approach, right? Where maybe you don't necessarily retrieve every time, but just let's say maybe be a bit more efficient, right, in terms of how you generate things and whether the prediction should be made by a model or let's say the retrieval document, right? They have, I think, made it more explicit, right, by adding these tokens. But I think in your approach, it's more implicitly handled, right? Like that's the difference I assume, right?
Exactly. So I think so yes, in our approach, it is more implicitly handled. And I think actually probably like in the future, like for the sake of like system interpretability perspective, handling that explicitly could potentially be useful. Yeah.
I see. And also, so one more thing. So let's say in your case, right, when you are trying with different models, right, and you say that it's bigger is better, right? But is it also the function of like, let's say, the number of tokens that's trained, or so is it like models which needs to be bigger, or it's like the models which needs to be more stronger, right, in terms of the performance?
Yeah, I think that's a great question. So yes, so I think for the set of like scaling law experiments, I show there, like I show like the larger the language model, the performance can be better on certain tasks. Yeah, so it could so yes, so it's basically like the parameter size there is like a proxy for the capability of the base model. And like for example, I think you're right. So for example, if I have a 7 billion model which is trained with way more tokens compared to my 30 billion model, and like I already found that on even on reasoning tasks, the 7 billion model is performing comparable to my 30 billion model, then I think in that case, yes, they are probably going to be equivalent. So I think basically in that experiment, I was just trying to show that I think there are certain things which is just adding non-parametric memory probably doesn't improve, but like it possibly can be improved by like training my model longer, or like using some better ways to train my model parameters.
Also, so do you have any thoughts on how to make the current approach more interpretable or at least explainable, like on how the decisions are made? So maybe let's say, so like in your setup, like right now, it's kind of implicitly deciding, right, whether it should focus on the retrieval documents or not, like, and let's say then make a prediction. But how can we make it more interpretable or at least explainable, right, and making decisions?
Yeah, so I think this is a very interesting question. So one thing, like I was thinking, so if I'm actually making a product or something, like making the current model more interpretable, so I was thinking like so for example, for the current model, probably I will not show all the retrieved passages to the user, right? So like when the user is using my current model, it will just see like the prompt and like the model generation. And I think probably like the augmented part, it will be implicit. But one thing, if just with the current architecture, potential things we can do is like, so for example, like we can still record the scores for different augmented prompts. And then probably like we can basically select the passages that contributed the most from the backend, and then like generate that as a citation. So I think that's one thing. I can think of. So basically, although like we handle things implicitly, we can still like find the relevant passages through the scores and other things in the backend.
So it's just more like using some saliency methods or at least some ways, right, where we see which particular section is more activated or at least where the attention is more prominent, right, and maybe make a call, right? That's it.
Yeah, so like you're saying, like using attentions, like maybe to find like relevant segments from the retrieval text chunks, and I think even from the final prediction, like so I think different passages, for example, like it will. So basically, different passages will contribute. So for the language model to generate different things. For example, if like different passages generate multiple answers, and like maybe I can show like the more certain ones.
Mm-hmm. So is this approach like, let's say, currently it seems more like a single hop approach, right? Like where maybe you do, let's say, all the passage retrieval, right? And then maybe like, let's say, do use that passages and like do the reasoning, right? But let's say if I want to probably use this as a more of a multi-hop setup, right? How can one extend that, like, so to multi-hop, right? Like, or it is like this.
Right. I think so. If I remember, so for example, I recently read like Arcari's very interesting self-reg paper. So I think that's a potential direction of how to expand it to like multi-hop. So we can basically like, so instead of so in my case it's like we just fine tune. So it's focusing on like how do we teach the model to better comprehend the context, but we can also like basically design instructions to fine tune the model to break down a question. And also like we can prepare like instruction fine-tuned questions with like basically multi-turn interaction. So I think that's like some extension I have on top of my mind. Yeah.
I see. And regarding like, so like the few shot results being like poor or at least not much, like let's say there is not much improvement, right? Is it like, so what is your intuition in, is it like due to the way the fine tuning strategy works, like more like a zero shot fine, so where you just pack everything and like you do fine tuning, or is it like if you do this fine tuning in a few shot setup, then maybe that would benefit potentially the
Yeah, so I think there could put so I think I will answer the question for two parts. So for one thing, I think so we didn't see improvement over future stress setting or like very small improvement. So I don't see that as a like a weakness of the model that bothers me, because I think one thing is like, for example, lots of the real world downstream use case like assistant. So most of the interaction is in a zero shot scenario. So I think, so first of all, like improving the zero shot performance is important. And second is like, although we didn't improve few shot performance, we also didn't see strong degradation of few shot performance. Mm-hmm. So which like the model still have like few shot or like in-context following ability. So I think these two like combined doesn't strongly concerns me. And regarding like whether, so I think there's room that we can like, for example, perform like few shot oriented fine tuning to improve improve few shot. So there is actually a related paper, like, so for example, like from University of Washington. So there's a paper called in context. It's called meta ICL, meta in context learning. So basically fine-tune the model so that they have better in context learning abilities. So I think people have done that. In my own experience, we found sometimes there is a little bit complexity of using basically this approach of like creating few shot prompts and find instruction in the model to follow them. So in the sense that like usually few shot prompts, you have a longer prompt portion in the prompt. So the answer part is a small portion. So you have a very much longer prompt. So usually when you have few shot fine-tuning examples, your fine-tuning signal becomes more sparse. And basically with the same batch size and steps, your model sees fewer number of examples. So we found that like there is a little bit difficulty of adding few shot examples into the fine-tuning process in our previous experience. So we didn't try it this time, but I think it's something potentially worth trying. Just keeping like these kind of like tiny, these tiny like maybe efficiency degrade like in mind.
Okay. Also, so in your setup right now, you're just doing standard causal language modeling, right? Fine tuning, or like, or did you also try maybe with like let's say some other approaches like prefix fine tuning, or at least like?
Yes, we didn't try that. Yeah, so especially prefix fine tuning, we didn't try. So like when I was saying parametric efficient fine tuning, I was thinking about adapters. Yeah, but
Could you repeat last part? Maybe I was lost.
Okay, so I was just saying, like when I was previously mentioning parametric efficient fine tuning, I was thinking about adapters.
I see. Yeah, adapters is also one, but I think in general, maybe prefix fine tuning also I think seems more logical here, right? Because you might want to attend to everything, right, into the context rather than left to right, right? At least the user prompt, right? And then basically generate the answer. So maybe there might be some better likelihood of, like, let's say, uh, like longer tokens like attending to each other, right? Basically, maybe which are like, let's say, on either extremes, right? Basically, due to this bidirectional nature. So yeah.
Yeah, I agree. I think that could be interesting to try.
Also, yeah, one last question. So, were there any experiments based on the data scales that you try? So, maybe like let's say with your setup, the way you did train, right, the objectives, is it like these objectives explicitly require lower data volumes than let's say other systems to get like near to same point, or like yeah. So, whether this like the approach that let's say you have, right, is more sample efficient in terms of like or like yeah. Any thoughts on that?
Actually, a great question. So I think in our paper, we adopt like basically a sample efficient paradigm. So we especially say, so I think the approach is like showing effect like without fine tuning a lot of data. So yeah, so I think so like we primarily experimented with this like sample efficient paradigm where like we select high quality fine tuning data with like good supervision signal and fine tune the system. I think so, and it's also specifically targeting for scenarios where people want to improve their retrieval-augmented language model, but also probably also don't have like lots of compute resource to perform like continuous pre-training, for example. So I think if we're just talking from system improve or performance improvement perspective, I think more compute could also help such system. And for example, like I think several retrieval-augmented language models are just proposed for pre-training. So like Retro, like Atlas from Meta. So I think in this case, like so basically kind of similar signals we use for fine-tuning here we can also like basically generate those from pre-training data. And I think if we have the resource, it could be like a step which is worth doing. So like maybe we do like retrieval-augmented pre-training as a first step before retrieval-augmented fine-tuning. So I think more compute could still help such system if we don't have resource limitation.
Awesome. Thank you so much. Yeah, I think that's probably all the questions that I had. Yeah. Maybe if anyone has any other questions. So I think, yeah, then we can probably, yeah, I think I don't see anyone having any questions. So yeah, we can maybe then, yeah, end the talk. Yeah, thanks for like presenting. It's wonderful work.
Thank you. Yeah, I'm also happy to answer any questions through email, so feel free to reach out.
Sure.
Thanks, everyone.